In this video, I want to talk about the Boltzmann equation. So we want to start with some basic concept. So a star is composed of gaseous plasma containing both neutral and ionized atom as well as free electrons. So these free electrons come from a process called ionization. So what does ionization mean, right? So for example, you take a hydrogen atom. So a hydrogen atom has one proton and then one electron, right? Negative, positive, right? So the process of ionization is when the electron leaves the hydrogen. So when does that happen? Well, that happens when the electron receives enough energy. So for example, the hydrogen atom could be around a young and hot stars that's emitting a lot of energy, and that energy hits the hydrogen. It gives it so much energy that it releases the electron. So that process, which we call the ionization, right? So we can say that the energy has ionized the electron from the hydrogen. So what you are left is this electron going off. So this now becomes a free electron, and then there's just one proton left for the hydrogen, and the exact amount of energy for a hydrogen atom to be ionized, so for the electron in the hydrogen atom to leave the proton is negative 13.6 eV. So we'll just talk about that later, right? So that's the process of ionization. So in the case of carbon, right, we call a neutral carbon C1. So this is a neutral carbon. So a neutral carbon is a carbon that haven't had one of its electrons stripped away from it. So C2 in the other case will be a singly ionized carbon. So what this means is that in this C2 scenario, one electron has been stripped away from the carbon atom. So it keeps going on like this, right? Until there's no more electron to strip, right? You strip away every electron and there's only the nucleus left at the end, but that requires a lot of energy. But you get the notation here is that when you have C1 or Ci, that is the neutral carbon. When you have Cii, so two of them, that's the singly ionized. When you have three of them, that's when you take two electron away, right? So that's how the notation goes. So the field of statistical physics shows that atomic energy level of a given ion is populated inversely exponentially as a function of their energy. So lower energy levels are naturally more populated than higher energy levels. And this is the reason, because a fundamental part of our nature is that systems tend to minimize their energy. And when you have a let's say a hydrogen atom where the electron is being at a higher energy level, it is generally less stable compared to a ground state hydrogen atom where the electron is at the n equal to 1 ground state, right? So when the electron moves from n equal to 1 to n equal to 3 or n equal to 2, it goes into a higher state and becomes less stable than the ground state. So a fundamental part of statistical mechanics and nature in general is that system will try to minimize their energy. So they want to be as stable as possible. So they will naturally fall back into the ground state in that process. So that's why the reason lower energy levels are naturally more populated than higher one, because they're more stable, and nature prefer more stable, and nature try to seek way to minimize the energy in that process. So this being said, a bound electron can be excited to a higher energy level by two processes, right? So if we have a hydrogen atom, again, I'll just draw it, right? So let's say this is at n equals to 1. So it's at ground state, it's a neutral hydrogen at ground state, right? So this can move to a higher energy level. It can move to n equal to 2, n equal to 3. And this happens when there's energy being applied to the hydrogen atom. And there are two reasons that this can happen. Like there are two main processes that can cause the electron to go from n equal to 1 to a higher energy level. So these two processes, right? The first process is the case of collision. So these electrons can change level when they collide with another particle, for example, a free electron. So in this case, maybe you have huge chunk of hydrogen, and some chunk of that hydrogen like has been ionized, so the electron has already left the proton in the middle, right? So the electron becomes the free electron, and then it collides with another hydrogen, causing that particular hydrogen atom's electron to jump to a high level. So that could happen. So that's the first process, which is the process of collision. So there's a second process that can cause the excitation of an ion, which is the absorption of a photon with energy equal to that of the electron transition. Because remember, when an electron moved from one energy level to another energy level, so in this case, maybe from n equal to 1 to n equal to 2, right? It takes a certain amount of energy for it to do that. And the energy could come from the absorption of a photon, right? So that's the second process, where it can go. So now we can talk about the Boltzmann equation after we've gone through some of the basic concepts. So the Boltzmann equation goes something like this. So let's write this Boltzmann equation. N I N J is equal to G I G J e to the power of negative E I minus E J over K T, where the K here is the constant, right? T is the temperature, and then what you have above is EI minus EJ, which is the energy difference. So K here is the Boltzmann constant. This Ni right here, what does it stand for? It stands for the number of atoms per unit volume in energy level I of the iron. So basically, put in simple term, it tells you how much electrons is in a particular level you want to choose. So what can this equation do? What can it tell us? Well, like it can tell us, for example, if you want to know, for example, hydrogen, right, at a temperature of, let's say 6,000 Kelvin, what percentage of that hydrogen atom, what percentage electron is in the, well, actually a better example would be maybe carbon, right? Like take carbon at 6,000 Kelvin. So what percentage of electron at a 6,000 Kelvin temperature would be in the n equal to 1 compared to n equal to 2? So what Boltzmann equation does is that it tells us how the temperature changes the amount of electron occupied in each energy level. So and then the G here stands for the degeneracy of this level. I'm not going to go too deep into that, but the degeneracy of an energy level is the number of quantum states with the same energy. And the quantity energy EI minus EJ here is the difference between the two energy ratio, right? Because EI and EJ are two chosen energy level. Like for example, for the carbon, you want to ask, for the neutral carbon, you want to ask, okay, how much electrons is in n equal to 1 right now, and how much electrons is in n equal to 2 right now, right? So to answer that question, well, you want to know what temperature it is at, right? So you know that first. Now you know the energy difference between n equals to 1 and n equals to 2, right? So that's what the term above is for. And then there's the degeneracy, which is, I'm not going to go too deep into that. So by calculating all of that, it gives you the ratio. It gives you the ratio of how much electron is in the state, is in the energy level n equals to 2 versus n equal to 1, right? So this equation, what it does is it gives us the ratio between two energy level, like how much electron occupies this energy level compared to another energy level. And right, to calculate that, we need the temperature and the energy difference between them. So that's a quick summation of this Boltzmann equation. So however, this form of the Boltzmann equation is not often useful. Instead, this form is used. So I'm going to talk about this form, which is U ion equal to sum n equals to 1 infinity Gn E negative En Kt. So this is the partition function. And then the better form of Boltzmann equation would be, so a better form of Boltzmann equation would be Ni over N ion equal to G I U ion E to the power of negative EI KT. Actually, I think the order should be like this, right? I should move this to the left side, so it's more intuitive this way, because u iron is part of this equation, not that this equation is part of u iron, right? So it's more, it makes sense I move it like this way, right? So this is our so this is our new Boltzmann equation, and then in this equation there's a term called u iron, which is given to the by the equation on the right. So what does this equation give us then? Like, what does it give? Well, what it gives is that, remember, the Boltzmann equation that we have just talked about give us the ratio between two individual levels. So n equal to 1 and n equal to 2. So two levels, the ratio between them. So what this form gives us is that a particular energy level ratio to the entire spectrum. So instead of saying in the Boltzmann equation case, like you could say in the previous equation case, you could say, well, what's the ratio between electron that's in n equal to 1 compared to electron in n equal to 2? So this equation instead tells us what is the ratio of electron in n equals to 2 compared to the entire spectrum, because remember there's an infinite amount of energy level, right? So what this tells us is that what is the ratio of, what percentage of the total electron that is in that particular level. So you can see how these two equations differ. The first one is comparison between two individual levels. The second one, which is the one I just wrote, is the comparison between one chosen level in the entire amount of electron across all the energy levels. So that's the difference between them. And to better understand these concepts, it is instructive to apply them to a hydrogen. So for hydrogen, we have a formula for its energy level. So En is equal to 13.6 1 minus 1 over n squared. So what does this formula give us? This formula gives us the amount of energy for different energy level, right? So if, like, for example, in the case of if you want to figure out what's the energy level difference between level n equals to 3 versus n equals to 2, right? So you just have E3 minus En. So E3 minus E2. Like, what this equation tells us is the energy of the electron in the nth level for a hydrogen atom. Remember, it's in hydrogen atom, because before I talk about the process of ionization, right? So for this equation, mathematically, you could see that the number could never get bigger than 13.6, right? Because no matter how big n's get, as it even approach infinity, this number will never exceed 13.6, because 13.6 is the amount of energy it takes to ionize, right? If the energy that is fed went beyond 13.6, it would have ionized the electron instead of making it go to a higher energy level, right? So if I sub into E2, so this basically tells the energy the electron has at the level of n equal to 2, like similar to n equal to 3. It tells the energy the electron has when it's at the energy level is n of 3, right? So the difference between them would be E3 minus E2. So that's quite intuitive. And then now we go back to this partition function and what it implies. So what is this u iron? What is this partition function? Well, this partition function, first, to calculate this partition function, an infinite number of terms related to the energy level must be summed, right? This partition function is a sum over all the possible energy level of an atom, right? And then when you try to sum all the possible energy level of a atom, right, you realize that the energy level there can be is actually infinite, and that's a problem, right? Because for very large values of n, so for very large values of energy level, the degeneracy increases rapidly, while the exponential found in this partition function equation, this exponential here tends towards a constant value. Then the sum will then converge for any temperature. Luckily, there isn't an infinite energy level in a physical sense for some reason. So for this reason, I'm going to talk about here. So, for example, according to the Bohr model of the atom, the radius of an atom level n is given by r is equal to a0 times n squared, where this A0 is a constant, 0.5298. I'm not going to go too deep into here, but basically this formula gives the radius of a hydrogen atom in level n, right? So now imagine what will happen if n were to be infinite in this case, right? Well, it can never be infinite, because an infinite energy level in this case would imply an infinite radius, right? But physically that's impossible, because as the energy levels goes up and up and up and up, eventually it will reach into another nucleus, right? Because this model will only make sense if the atom in question is alone in the universe, which is obviously not the case, right? Our universe does not only have one atom in the center. There's a lot of hydrogen clumped together, and the radius therefore cannot be infinite, because if the radius get infinite and the electron just keep getting higher and higher, if you were to imagine that case, then eventually it's going to step into another hydrogen's territory, right? So nature's law forbid that, right? So that problem is solved. So then, if we were to not deal with this problem of n being infinite, so n being infinite is not a physical reality. So if we were not to deal with that, then we can approximate the partition function, which is, again, to be reminded, the sum of all possible energy level of an atom, to be approximately this function right here. And then you might ask, what is the point of even talking about this sum over all possible energy level of an atom, right? But remember what I just talked about. This formula right here is calculating the ratio between electron at a specific energy level versus all the entire other energy level. So there's got to be a way in this mathematical equation to find a way to represent the energy in all possible energy level other than the one that you have chosen, right? And that way is given by this partition function. Is what this partition function is for. That's its part in this equation, is to give you the sum over all possible energy level of an atom, right? And that's important when you try to calculate the ratio between an individual level versus all the level, right? Because like what I just keep repeating it, because it's quite important that you see why this is relevant in the case, right? You want to try to calculate one electron, the energy level ratio versus the entire other energy level, right? Then you need an expression to sum up the entire possible energy level of the atom, which is what this partition function does. So for this lecture, I'll go as far as this, but in my next lecture, I'll keep going deeper and dive into more details of this Boltzmann and Saha equation concept.